Welcome, fellow physics teachers, to another activity-filled episode of your TV program, Physics in Everyday Life. In the previous episodes, we described the motion of a single particle such as stones and balls, and we were able to build up the idea of order and predictability in nature. By means of equations such as S is equal to 1/2 gt squared, we were able to predict where a falling body would be at any instant of its fall. And this predictability on a large macroscopic scale is used in space exploration, in sending satellites into outer space. In the last two episodes, we studied the mechanical properties exhibited by matter in the bulk. We studied the properties of elasticity, pressure, and buoyant force by observing the behavior of a certain object or of a volume of matter. It was mentioned that these properties arise because of the forces of interaction among the particles that make up matter. In today's episode, we will consider the particle nature of matter. We will focus on a particular science process called modeling. Based on some observations, we shall develop a kinetic molecular model of matter. We will concentrate on the kinetic molecular model of gases to explain pressure and temperature and their relationships in terms of the model. So stay tuned, and we will be back for today's episode on molecules in motion. Welcome back, fellow physics teachers. Let us begin today's lesson with a demonstration. Watch what happens when I drop a small amount of ink into the water here. Is there any difference whether I drop the ink on the water surface like this, or at the bottom of the glass, like this? Also, why does ink blot on paper? The fact that the ink spreads out indicates that ink consists of particles which can occupy space available to them. We can also infer that paper and water consist of particles with spaces between them. These particles are what chemists refer to as molecules. We have seen that although a solid object is rigid and has a definite shape, it can be deformed with the application of a force. In the case of liquids, we have learned that they are incompressible, but they easily flow. Based on these facts, what picture can we make? Well, we can create this model for solids. In this model, the balls here represent the molecules, and the molecules are arranged in an orderly array. In between the molecules, we have springs here to keep them in place. This model can account for the definite shape and rigidity of solids, and it can also explain the elastic property of some solid materials. On the other hand, we can picture liquids as made up of molecules which can slide past one another, like this model here. The molecules can be easily poured, and they take the shape of the containing vessel. Okay, watch this. And so we have here molecular models for matter in the solid and the liquid phases. What about matter in the gaseous phase? Recall some common observations on gases, and we will answer this question after this short break. Don't go away. Fellow physics teachers, we're back, and in the next few minutes, we shall recall common observations about gases and use them to come up with a model. Let us consider the following situations from which we can infer a model for gases. Alcohol or perfume vapor that reach a person from a far distance in different directions indicates that the molecules of alcohol vapor are in random motion. The fact that the balloon deflates means that the air from the balloon has occupied the empty bottle. The air molecules must be farther apart because they are now occupying a much larger space. That the molecules of gases are very far apart compared with those for liquid is supported by the data that the volume of 1 gram steam at 1 atmosphere is 100 times the volume of 1 gram water at 1 atmosphere. The observation that air in a tire exerts a high and constant pressure suggests a large number of molecules which are perhaps in continuous motion. A theoretical model of gases can be evolved from these inferences. Such model is called the kinetic molecular theory model of a gas. A physical model can be built based on the theoretical model. The following assumptions constitute the theoretical model. 1. Gas consists of many identical particles which move in accordance with Newton's laws of motion. 2. The particles move in continuous random motion. 3. The particles are small and they are very far apart. The distances between particles are long compared to their sizes. 4. There are no forces of interaction among the particles except when they collide. 5. No kinetic energy is lost when particles collide with one another or with the walls of the containing vessel. This means that the collisions are perfectly elastic. Let us now use the model to give meaning to pressure exerted by gases. In the previous episode, you learned that air exerts pressure in all directions on the walls of the containing vessel, like this inflated balloon here. Where could this pressure come from? Let us consider a single molecule inside a cylinder where it is in continuous motion along the x-axis. According to our model, collision with the walls of the cylinder are perfectly elastic. No kinetic energy is lost, and so the molecule will forever be colliding with the walls. Every time the molecule collides with the left wall, a force equal to F, equivalent to delta mv over delta t, is exerted between them. If there is a large number of molecules inside the cylinder moving towards the wall, we can consider the average number of collisions the molecules make with the wall. This gives us the average force exerted by the molecules on the wall due to collisions. If this average force is divided by the area of the wall, the result is equal to the average pressure exerted on the wall, or this is P equal to F over A.